Okay, so I've got a few questions for you. Now, on the surface, they're going to sound completely random, totally unrelated. But trust me, there's a secret mathematical thread that connects them all. And it's a thread that, believe it or not, kind of runs our modern world.
All right, first up, how many shuffles does it take to make a deck of cards truly properly random? Okay, now for a much more serious one. How much uranium exactly do you need to build a nuclear bomb?
Number 3. This is something you probably do a dozen times a day without thinking. How does Google know, really know, which web page you're actually looking for out of billions? And last one, how does your phone do that thing where it predicts the very next word you're about to type? So shuffling cards, nuclear bombs, Google search, predictive text. What in the world do they have in common? Well, the answer to all of them, believe it or not, goes back to a bitter, century-old feud between two mathematicians. So let's set the scene. We're going back to Russia in 1905. The whole empire is just simmering with tension. You've got socialists rising up against the czar, and this political chaos, it infected everything, even, weirdly enough, the academic world of mathematics. At the heart of this was a guy named Pavel Nekrasov. He was the big shot, the tsar of probability, and he had this, let's call it a philosophical idea. He argued that when you see statistical patterns in society, that's mathematical proof of free will, that people are making independent choices. But his rival, a fiery atheist named Andrei Markov, they literally called him Andrei the Furious, thought this was just completely ridiculous. Markov's whole point was, look, you can get predictable patterns even when events are dependent on each other. It has nothing to do with free will. So what were they fighting about? It all came down to this one idea, the law of large numbers. You've probably heard of it, right? It's pretty simple. If you flip a coin a bunch of times, the more you flip it, the closer your results are going to get to that perfect 50-50 split of heads and tails. For like 200 years, the assumption was that this law only worked for things like coin flips, independent events, where one flip has zero impact on the next. Nekrasov took this law and applied it to people. He'd look at stats for things like marriage rates, and he'd see that they hovered around a stable average every year. And to him, that was it. Case closed. That's mathematical proof that every marriage is an independent act of free will. And Markov, well, he thought this was just terrible logic. So he decided he was going to prove Nekrasov wrong, once and for all. So to tear down Nekrasov's argument, Markov needed to find a system where the events were super obviously dependent, where one thing clearly influenced the next. And his idea was just brilliant. He looked at the letters in a book. Think about it. The letter H is way more likely to be followed by E than by X, right? It's a perfect example of dependent events. So he got to work. He took a famous Russian poem, Eugene Onegin, and he painstakingly analyzed the first 20,000 letters. He calculated that if the letters were totally independent, like Nekrasov's free will choices, then a vowel should follow another vowel about 18% of the time. But what did he actually find? It only happened 6% of the time. That was it. That was a smoking gun. The letters were undeniably, mathematically dependent. And from this data, he built something revolutionary, what we now call a Markov chain. He basically created a little prediction machine. It had two states, vowel and consonant, and he fed it the probabilities he'd found, the chance of a vowel being followed by a consonant, and so on. Then he just let it run. And what happened? His simulated text, generated by these dependent rules, ended up with the exact same ratio of vowels to consonants as the original poem. He had done it, and that was the final blow. Markov had proven, beyond a doubt, that you could have a system of dependent events that still obeyed the law of large numbers. He completely shattered Nekrasov's whole argument connecting statistics to free will. He'd invented this whole new branch of probability, and here's the crazy part, almost nobody cared. At the time, it was just some obscure academic smackdown. The world just moved on. Until decades later, World War II. In the deserts of New Mexico, inside the top-secret Manhattan Project, a brilliant mathematician named Stanislav Ulam was staring down an impossible problem. And the key, it turned out, was Markov's forgotten idea. So Ulam was actually recovering from a serious brain infection that almost killed him.
And to pass the long hours, he played a ton of solitaire. Being a mathematician, he started wondering, what are the actual odds of winning a game? He realized that calculating it directly was, well, you see that number on the screen. It's basically impossible, hopeless. But then he had this flash of insight. What if you don't calculate it? What if you just play a few hundred games and see how many you win? You could approximate the answer. A beautifully simple idea that would change everything. So he takes this idea back to his work at Los Alamos. He and the legendary John von Neumann realize they can apply this to the problem of neutrons inside a nuclear bomb. See, a neutron's path isn't random. What it does next depends heavily on what it just did. It's a chain of dependent events, just like Markov's letters. So they created simulations running thousands of these chains to see what would happen. And by doing that, they could figure out if a chain reaction would sustain itself. They could solve for critical mass. And they gave this powerful new technique a code name, the Monte Carlo method.
Okay, let's jump forward again. It's the 90s. The World Wide Web is exploding. There's information everywhere, but finding the good stuff is a total nightmare. Early search engines like Yahoo basically just counted how many times a word appeared on a page. It was clumsy and super easy for people to game the system. The real challenge wasn't finding pages with the right words, it was finding pages with real quality. And then come two Stanford PhD students, Larry Page and Sergey Brin. They had a groundbreaking idea. What if you thought of the entire web as one enormous Markov chain? They imagined a random surfer just clicking on links. A page's importance, its rank, would simply be the amount of time that surfer ended up spending on it. This was revolutionary. It meant that a link wasn't just a link, it was an endorsement. And a link from a really important page, that was a massive vote of confidence. So, look at this simple example. Ben's page comes out on top. Why? It's not just about the links on his page. The key is that he gets a link from Amy's page, which is also considered important. It perfectly illustrates their core principle. It's not about how many links you get, it's about who is linking to you. That simple, elegant idea was the heart of PageRank, the algorithm that turned Google into an absolute giant. Okay, so now let's bring this all the way back to the beginning, back to Markov and his letters. Because around the same time the Monte Carlo method was being developed, another genius, a man named Claude Shannon, you might know him as the father of information theory, dusted off Markov's original concept. Shannon took Markov's idea and leveled it up. Instead of predicting the next letter, he built chains that predicted the next word, based on the words that came before it. Now, the results he got, they were mostly nonsense, like this sentence right here. But if you look closely, you can see little fragments that almost make sense. It's like the ghost of grammar is there. And this experiment, this was the seed. This was the conceptual starting point for the predictive text on your phone, and yes, for the large language models that are completely transforming our world as we speak. And that brings us right back to where we started. That very first question, how many times do you actually have to shuffle a deck of cards to make it random? Well, if you're a card shark who can do a perfect riffle shuffle, where the two halves interleave one by one perfectly, the answer is just 7. A surprisingly small number, right? That's because each shuffle is just one step in a Markov chain, and after 7 steps, the system gets so mixed up, it's considered random. But what about the way most of us shuffle? That clumsy overhand shuffle, where you just kind of drop clumps of cards. Well, to get that deck properly random, you would need to shuffle it over 2,000 times. No, that's not a typo. 2,000. The math behind it is just that powerful. So there you have it. Google's search algorithm, the physics of a nuclear bomb, the AI on your phone, and even shuffling a deck of cards. They all rely on the exact same mathematical idea. An idea born from a bitter, personal feud over the nature of free will. Isn't it just wild to think that this angry argument gave us the fundamental tool it now predicts, organizes, and pretty much runs our entire digital world?